In this videocast, we'll look at atom composition, symbols of elements, atomic weight or mass, and a little introduction to the periodic table. First, atoms. Atoms are composed of three main subatomic particles. The first one is called an electron, which has a -1 charge. The second part is called a proton, which has a +1 charge and resides inside of something called the nucleus, which is the center of the atom. The third part is called a neutron. Neutrons also reside in the nucleus of an atom and have a similar mass to protons. The protons and the nucleus together make up something called the nucleus. As we'll learn, especially when we delve into Chapter 6, the protons and neutrons make up most of the mass of the atom, whereas electrons' mass is mostly ignored. We also find that the electron is very difficult to pin down as to where it is residing around the outside of the nucleus. It encompasses a large volume compared to its size, and therefore most of an atom is made up of empty space. Secondly, we'll look at symbols of atoms that make up the elements. On your advanced placement exam, you'll get a periodic table similar to something like this. Notice the periodic table has some symbols on it. It also has some numbers associated with it. But what's more important, look at what's missing. There are no names for any of the symbols on the periodic table. Those are assumed that you've memorized and become very used to. The symbols on the periodic table also have some numbers associated with each one of them. And if we look at the key, we can see that the symbol on top of the number is called the atomic number, and the symbol below it is called the atomic mass, sometimes known as the average atomic mass. This is all the information you're given on what I like to call the crappy periodic table, because it's kind of crappy compared to some periodic tables where you can get tons and tons of information. A symbol of an atom or of an element is given in its complete form when it describes the number of protons and the number of neutrons in the element. For example, magnesium, the element magnesium, with a 24 up above it in the upper left-hand corner as a superscript and the number 12 in the lower left-hand corner as a subscript, indicates to us the number of protons in the nucleus, which is known as the atomic number. Please be aware that the atomic number tells us the number of protons in the nucleus. Protons in the nucleus. And the number 24 tells us what's called the mass number. It's called the mass number because it gives us an approximate mass, not the actual mass for an average atomic mass, but the mass of one atom just with the addition of the protons and the neutrons. The mass number is the protons plus the neutrons in the nucleus. This equals the mass number. MN stands for mass number. So if you know the atomic number, or simply if you know the symbol of the element and look up the atomic number on the periodic table, you can figure out the number of neutrons in the nucleus. Remember, this symbolization is used to illustrate that there are different isotopes, atoms with the same number of protons but different number of neutrons, for a number of different elements. Another way of writing this isotope of magnesium is to write magnesium-24. The 24 right here, remember, tells us the mass number, and it tells us the number of protons and neutrons in the nucleus. So, with the name magnesium-24, or with the symbol magnesium-24-12, how many protons, how many neutrons, and how many electrons are in this element? Well, the number of protons is easy. It's the number in the lower left-hand corner. It's the atomic number. So the number of protons is 12. The number of neutrons is a little bit more difficult to find because the number of protons plus neutrons is given to us by the number in the upper left-hand corner. We can say that protons plus neutrons is equal to 24. If we know the protons are equal to 12, now we can write an equation that says 12 plus some number n is equal to 24. And if you're pretty savvy at math, you can do this in your head knowing that the number of protons then would be equal to, the number of neutrons would then be equal to 12. Lastly, how many electrons are in this? Well, we'll find in next videocast that there's also a third number that goes in the upper right hand corner of a symbol of an element if it has lost or gained electrons. If there's no number there, then the number of electrons is equal to the number of protons because the atom is electrically neutral. So if there's no number written in the upper right hand corner here, a positive or a negative charge as it's going to be called, then the number of electrons equals the number of protons, and therefore the number of electrons in this atom of magnesium would be 12. Let's do a couple more examples. Let's say, for example, we have the symbol Au-197. How many protons, how many neutrons, and how many electrons are in gold 197? Well, the first thing you want to do is look on your periodic table and find the element gold. The element gold happens to be down in this corner right here, Au-79. And if you didn't know that Au is gold, that'll be one of the things you'll have to memorize in the next few days. Gold has an atomic number of 79. And remember, this atomic number right here tells us the number of protons in the nucleus. The number of protons in the nucleus. So when it asks us how many protons are there, we can say that there are the atomic number's worth, which is 79. This number 79 could also be written right down here. In this case, just to make it a tough problem, it's not. And therefore you have to look it up on the periodic table. How many neutrons are there? Well, to find the number of neutrons now, you need to take the mass number, 197, and write a little equation saying 197 is equal to the protons plus the neutrons. Well, we know from looking on the periodic table the number of protons is 79, and the number of neutrons is something that you have to solve for. And if you do the math for this, 197 minus 79, you find out that there are 118 neutrons in this isotope of gold. Lastly, how many electrons are there? Remember, I said that there could be a small number in the upper right hand corner. If there is no number, we assume it's 0, which means that the protons are equal to the electrons, and therefore there are 79 electrons in this isotope of gold. This is because it is electrically neutral, and the positive charged things and the negatively charged things cancel each other out. How many protons, neutrons, and electrons are there in strontium-90? Now, if they just give you this symbolism, first thing you want to do is look on the periodic table and find the element strontium. Strontium is located in the lower left-hand corner of the periodic table, and if you zoom in on this, you can see that strontium has a atomic number of 38, meaning that it has 38 protons. So, in answer to this question, we have protons equal to 38, and if we wanted to find neutrons now, neutrons, we would have to take the mass number, 90, and subtract from it the 38 protons, and what's left over would be our neutrons. So 90 minus 38 would give us 52 neutrons. Lastly, how many electrons are there in strontium-90? Well, since it's electrically neutral, it doesn't tell us that strontium is charged at all, which we'll see a little bit more about next videocast. The protons equal to the electrons, so there are 38 electrons. Give the chemical symbol for an element with 82 protons, 82 electrons, and 126 neutrons. When you're given a problem like this, what you need first to do is look up what element has 82 protons, because it's the number of protons in the nucleus that makes an element be what it is. So look on your periodic table, find the element that has 82 protons, and if I zoom in on this, you can see that element 82 has the symbol PB, 82 PB. PB is the symbol for the element lead, if you haven't memorized that yet. And so when you write the symbol for this element now, you write down PB, and you'll put the number 82 in the lower left-hand corner, because that's the number of protons there are in the nucleus. The last thing you want to write is the number of protons plus neutrons up here in the upper left-hand corner. And 82 plus 126 is 208. So put 208 up here at the top, because remember, that number is the number of protons plus neutrons in the nucleus. Now we'll learn next videocast that we could also put a number out here if the number of electrons and protons was not equal. Next, we're going to talk about atomic weight or atomic mass. And if you'd like to, you can open your textbook to page 47 and follow along with me. Today we can determine the masses of individual atoms with high degree of accuracy. For example, we know that a hydrogen atom has a mass of 1.6735 times 10 to the negative 24th grams. Not very much. As we noted earlier in the chapter, it's convenient to use what's called the atomic mass unit, AMU, when dealing with these extremely small masses. The atomic mass unit, one atomic mass unit, is equal to 1.66054, lots of sig figs there, times 10 to the negative 24th grams, an incredibly small number. The atomic mass unit is presently defined by assigning a mass of exactly 12 AMUs to the carbon-12 isotope. In these units, it then goes on to give us the hydrogen and oxygen mass. This relationship is based on giving the atom of carbon-12, an atom of the isotope carbon-12, exactly 12 AMUs. And that's simply by design, because there's a lot of carbon in the world. So how do we get to find out what the atomic weight or mass is of a whole bunch of atoms? Because remember, atoms are always a combination of several different isotopes. For example, on Earth, if you dug up a sample of carbon, you'd find out that most of it is carbon-12. As a matter of fact, 98.93% of carbon is carbon-12. Well, what's the rest? Well, it's carbon-13. Carbon-13 is made up of only 1.07%. Those are the two isotopes that make it together. So we can't say that the mass of a bunch of carbon would be 12 grams, or I'm sorry, 12 AMUs, and we can't say that it would be a mass of 13 AMUs. It's somewhere in between, because if we took a big lump, what we'd want to find is what's called the average atomic mass of a sample containing both of these. Now what we do is we find what's called the weighted average of the average atomic mass. Sometimes instead of calling it the atomic mass, it's called the atomic weight as well. So don't be shocked by using weight and mass interchangeably in chemistry class. We abuse those terms a lot, and to the dismay of many physics teachers. Average atomic mass. Here's a sample problem I'd like you to copy down, and if you need to, pause the video now to make sure that you have it copied down into your notes, and then we'll work the problem together. Naturally occurring chlorine is 75.78% chlorine, 35, which has an atomic mass of 34.969 AMUs, atomic mass units, and 24.22% chlorine 37. which has an atomic mass of 36.966 AMUs. Calculate the average atomic mass. Now, to find the average atomic mass, what we want to do is take what's called the weighted average. I'll write that down. The weighted average. Now, if you've ever taken a class in high school or in middle school where they say your grade is determined by 40% tests, 40% homework, and 20% citizenship, all of a sudden your entire grade comes from a weighted average, where it's 40% one thing, 40% another thing, and 20% another thing. How do you find the total of that? Well, that's what we're doing with a weighted average problem like this, where we have two different isotopes coming together. So to find the total average atomic mass, or the weighted average atomic mass, what we'll do is we'll take our percentage of chlorine, and I'm going to write it as a decimal now, 0.7578, and multiply that by the mass of chlorine 35, which is 34.969 AMUs. I'm not going to put the units in right now and break that rule just for a moment, because otherwise I'm going to run out of space. Then I'll add to that the percentage that is chlorine 37. The percentage, I'm going to write it as a decimal once again, is 0.2422, and I'll multiply that by the weight of chlorine 37, which is 36.966 AMUs. Now, I'll take this number, multiply them together in my calculator, take these numbers, multiply them together in my calculator, and I will get my weighted average. Notice 75% of it weighs this, 24% of it weighs this. I add those two together, and I get my average atomic mass, which turns out to be 35.45 AMUs. Notice that it should be somewhere between about 35 and about 37. As a matter of fact, it's closer to 35 than it is to 37, because 75% of it is closest to 35. If you look on the periodic table and zoom in on the element chlorine, which is in the upper right-hand corner in a group known as the halogens that we'll find out in just a little bit, notice the average atomic mass of chlorine is listed as 35.45. These numbers that contain decimals are the average atomic mass of all the naturally occurring isotopes of those elements. And they're listed always on the periodic table, and the method that we just used is how all of the average atomic masses are determined. You have several sample exercises and practice exercises like that to do. Let's take a little closer look at the periodic table and some of the things that make it up. First of all, we already talked about the symbols in each box and how the top number is known as the atomic number. The bottom number is the average atomic mass that we just found by using a weighted average. And then the symbol, always notices a capital letter and a lowercase letter. These symbols are universal throughout the world. And no matter what language is spoken, the same symbol is used with these letters to indicate what element it's made up of. Now you also notice on the periodic table that there is a dark line that separates a portion of the periodic table. This staircase, as some people call it, separates the metals, which are over on this side of the periodic table, from the nonmetals. The nonmetals are over here on this side. The metals are over here on this side. Elements that border the staircase, except for aluminum, are known as semimetals. Semimetals, or some people call them metalloids. Metalloids, because they have properties of both metals and nonmetals. Columns that go up and down are called groups, or sometimes they're called families. and certain groups or families have names. The rows that go across from left to right that are numbered over here as 1, 2, 3, 4, 5, etc. are called the periods. Periods are the things that go from left to right across the periodic table. And even though there's like a blank area here in the middle, the period does skip right across that valley and continue from left to right across. Notice these elements down here at the bottom. These are called the rare earth elements. They actually fit right into these two slots right here, where all of these elements would normally be put in there. Usually they're pulled out and put to the bottom because they're not used that often, and it also allows us to squish the periodic table together. When these are put into the space, it's called the long form of the periodic table. Now there are five groups or families you need to know the names of. These guys, sometimes known as group 1, are the alkali metals. And if you have a periodic table handy, I recommend that you write these things on the periodic table. If not, add them to a periodic table when you get one in class next. This group right here, the second group, is called the alkali earth metals. Alkali earth metals. The word earth is added to those guys. Alkali earth. Remember, these are the earth metals. These are just the alkali metals. The middle ones here, these guys are called the transition. And the transition metals are the ones that are generally noted for color in many compounds and solutions. They're all metals and all contain properties of metals. These groups over here, group 17 in particular, the one that has a 17 written on top of it, maybe you can't see real well, are called the halogens, as in like a halogen light bulb. As a matter of fact, there is a halogen used in the halogen light bulb. Fluorine, chlorine, bromine, and iodine are known as the halogens. This last group, group 18 right here, is known as the noble gases. Noble gases. This is helium, neon, argon, krypton, xenon, and radon. Those are the noble gases. This group right here, the oxygen group, also has a name. I believe it's called the chalogens, C-H-A-L-O-G-E-N-S, but it's rarely used. The four that you need to know, alkali metals, alkali earth metals, halogens, and noble gases, are the most important ones that you should have memorized the names of, and you should know the symbols and the formulas for many, many of these elements on the periodic table.